Okay, great. Yeah, so like Flora said, I'm a fourth year PhD student at Johns Hopkins, and today I'll be talking about our algorithm that we developed to fix oversplitting. So first, just a quick primer on template matching spike sorters. So usually these algorithms start with templates that are initialized either from a pre-existing library of waveform shapes, or you extract the threshold crossings from the current recording and then use those to initialize the templates. And then essentially the way these algorithms find the spike times is that they convolve the templates with the data and basically iteratively subtract the most matching section of the recording. And then they repeat this convolution process many times to extract each spike, and some spike sorters go back and forth between the convolution process and then refining the templates to get the best estimate of each neuron's waveform. And this process usually works better than traditional spike sorters. Classical spike sorters, which just use threshold crossings and then clustering in, for example, PC space, but they still have some limitations. So the main limitation is that because the template matchers learn a single waveform shape for each unit, they can't really account for changes in a unit's waveform shape. So if you have a neuron whose waveform changes due to biophysical reasons, a lot of times they will split that into multiple units. So some examples of what might cause the oversplitting. One reason is drift. So even though the actual action potential of the unit isn't changing biologically, the way that gets recorded by the probe changes due to changes in the relative position of the probe. So for example, in a real recording, you might see that two units with very similar waveforms, one of them has a firing rate that drops off at a certain point in the recording, and its firing essentially gets taken over by a different unit. Another reason for oversplitting might be bursting. So a lot of times due to the biophysics of spike generation, if you have a neuron firing very quickly in succession, the later spikes in the burst might show some attenuation of the amplitude, or the width of the spike might become larger. And then lastly, sometimes, especially with multi-shank probes, you might record different compartments of the same neuron on different parts of the probe. So here we see the first shank seems to be picking up the dendritic spike of this neuron, and the second shank seems to be picking up the somatic spike. And because template matchers cannot learn templates that aren't spatially contiguous, they have to split this into multiple neurons. So usually correcting these errors is a core part of manual curation, and especially for studies that are concerned with single neuron tuning properties, these are very important to the scientific findings. But as recordings grow in the number of channels and as people implant multiple probes simultaneously, the amount of time it takes to fix these errors becomes infeasible. So that kind of motivated us to develop SLAY, which is our algorithm to correct these errors. Essentially, the way SLAY works is by using metrics that quantify the same quantities that human curators would look at. So we have a metric for waveform similarity, one for spike time correlation, and then refractory period penalty. And we compute this metric for each pair of neurons, and the pairs of neurons with the metric higher than a certain threshold get merged together. So for the waveform similarity, we train an autoencoder network to essentially compress the spikes into a low dimensional waveform representation. So on the left here, we're putting in a spike that was extracted from the recording, and we sort this so that the peak channel is at the top, and the rest of the channels are sorted by distance from the peak channel. And essentially, we train the autoencoder to reconstruct the input spike while having a bottleneck in the network so that it has to represent the spike in a small vector of 15 numbers. And the advantage of this approach over things like PCA is that the nonlinearity in the autoencoder is better at representing complex waveform features. And then also because of the architecture of the convolutional neural network, it's also robust to small temporal shifts in the spike waveforms. So maybe if the template matcher didn't perfectly find the spike time, if it's off by up to 5 samples, our representation is robust to that. So here I'm showing a 2D visualization of the lane space of the autoencoder, and each dot in this plot is one spike. and we've colored them by kill sort cluster. So here you can see without the spatial information of where the spike is on the probe, there's some well-isolated clusters, but there's also a lot of overlapping. But if we reintroduce the information about the peak channel of the spike, we see a lot of good isolation. But even in this 2D visualization, we can still see that there's some errors that the template matchers make. So in the top row on the right here, we see there's some contamination where these clusters look separate, but certain spikes in each cluster are assigned to the wrong cluster. So especially this middle one here, where we have two very separate clusters, but the bottom of the top cluster is being assigned to the wrong cluster. And then we also see some oversplitting errors where certain clusters are almost completely overlapping, but Kilosort clusters them into separate units. So these would be the bottom row would be the types of errors that our algorithm fixes. So because we have this expressive waveform feature space from our autoencoder, we can essentially just use the distances in this latent space as an estimate of how similar the waveforms of the units are. So that kind of makes up the first waveform similarity metric. And then the idea behind the cross-correlation metric is that for independent clusters, their cross-correlogram should be approximately flat. And for clusters with correlated spike times, the cross-correlogram should be very non-uniform. So this is an example of a cross-correlogram from an oversplit bursting unit where you can see this very characteristic asymmetric shape with a very large peak. So basically to quantify how far this observed cross-correlogram is from an independent distribution, we use the Earth movers distance, which is essentially just a way to compare different distributions. So that makes up our second metric for spike time correlation. And then lastly, to make sure we don't perform merges that would result in contaminated units, we just use a standard metric for refractory period penalty, where we assess the probability that the observed number of violations is greater than an acceptable threshold. So we validated our algorithm across a bunch of different recordings with different animal models, brain regions, and probe types. And we also wanted to make sure that our algorithm worked on kill sort 2.5 and 4. So we sorted each recording with both algorithms. So first, just so that we had access to ground truth, we introduced some simulated oversplitting into each recording. So we had 4 types of oversplitting, one just randomly assigning the spike times to 2 clusters, one based on drift, so the probability of splitting changed depending on the time of the recording, one based on bursting, so we detected bursting neurons and put the later spikes in each burst into a separate unit, and one based on amplitude, where we split the amplitude distribution and put the lower amplitude spikes into a different unit. And looking at the results across both spike sorters and all 4 recordings, we found that SLAY has both a low false negative rate and a low false positive rate. So the proportion of true oversplits that SLAY found was very high across recordings, and the proportion of SLAY's suggested merges that were correct were also very high. And then we also quantified our algorithm's agreement with human curators on the original recording. So this is without the artificial oversplits that we introduced. And we found that SLAY achieved very high agreement with human curators, about 85%. And this is with a single set of parameters across all 4 recordings. And we also found that the number of merges is non-trivial, so it can be anywhere from 10 to 30%. And there doesn't seem to be a clear pattern where kill sort 4 is resulting in less oversplitting than kill sort 2.5, for example. Yeah, so just to conclude, our algorithm corrects oversplitting across a very wide range of recording conditions. The parameters in the algorithm are adjusted kind of based on personal preference and also how important single unit isolation is to downstream analyses. So for our paper, we use the same set of parameters for all the recordings, but you tune these based on the specific region or animal model that you're looking at. And then also the runtime of our algorithm is much lower than the spike sorting itself, mainly because our autoencoder network can be trained once per brain region and then reused across all the recordings that you take. And then finally, we currently have a standalone package that supports the Phi spike sorting format. but we're also in the early stages of integrating it into spike interface.